Welcome to Easy Gates Biomedical Gate 22 solutions. So next interesting problem of 56 using BHELs. Interestingly, two PNP transistors given. Yes, that's a problem figure along with the statements. In the given circuit diagram shown below, the BJTs are biased with VEB equal to 0.7. That's usually the expected data whenever the PNP transistor is given. So it's given for both, okay, transistors. You can label the transistors for clarity. It's Q1 and Q2. So given Q1 and Q2 are identical transistors with their VB, okay, VEBs instead of VBE. VBE by habit for NPN. This is for the PNP. VEB1 as well as VEB2 is equal to 0.7. Emitted to base junction must be for bias for PNP. So neglect the base current for operating point calculations. That means for DC, you can neglect. That means capital IB is saying 0. Okay, micro usually. So even in micro, he is allowing us to take 0 current. Assume infinite input and output impedances for the BJTs. Infinite input and output impedances for the BJTs. Infinite input means probably he means the AC base current is 0 and he means small r naught is equal to infinity. Okay, that's early effect resistance for the small signal equivalent of the PNP. Okay, so let us take this for this is for the DC and this is for the information for the AC analysis. Okay, yes, now the problem is the output voltage V0 with the small signal input, small input voltage VI. You can treat this as a small signal input VI 10 millivolt. Okay, so VA is like a AC, you can feel V in is equal to 10 millivolt. Let me take, okay. It's a DC, okay. So a DC voltage of applied around your Q point, okay. So then what will be the output voltage? V0 with the small input voltage. So there is no capacitor in this. So that's why he's going for usually in transistor amplifier circuit, we go with AC. So intentionally he's playing with the DC now. So it's a small incremental change is offering. So you take it as a incremental change in the Q point at the base and how it is going to make a change in your emitter of your second transistor that is given as V0. Okay, that's a expected output. Simply let me take this as an input voltage V in like a AC and this is the output voltage like a AC. Okay, so that's a AC small signal analysis we're going to perform. Then the thermal voltage for the transistors given, it is 25 millivolts. Fine. So we don't know the DC conditions. Okay, so problem actually belong to both DC as well as what AC analysis. So at the end of DC analysis, we need to show them they are active. Then we need to get their small signal equivalent, small RE1 and small RE2. Then we can begin a comfortable AC analysis to find out V0 due to Vn. Okay, so we'll find out V0 in millivolts. Okay, assuming a small incremental DC voltage applied at the input. Yes, let us perform a DC analysis first. So DC analysis, the first step, always switch off the AC signal. So let us switch off. So I'm making VI is equal to 0 volt. Okay, VI is made 0. Then we'll make a comfortable DC analysis. Then this point is given. Okay, so this is 0 volt and because the bottom rail is 0 already given. So this is 0 because of Vn is made 0. So then this point potential will be 1.1 volt. Okay, let me write it here. So the base of transistor Q1, this is transistor Q1 and this is transistor Q2 as per the labeling given. So the base is going to be at 1.1 volt. Okay, and we know VEB already given. This is going to be 0.7 volts. Therefore, from 1.1 potential raises. Okay, so it is going to become 1.8 volt. Okay, so then again potential raises by 0.7. Okay, so anyway it is okay. So yes, we can't play with this 2.5 volt because there may be some current. Okay, better let me go by this route. It's 1.8. Again potential should be for VEB another 0.7. Therefore it has to be 2.5 volt. If it is 2.5 and from 2.5 you're losing 2.5, is going to be 0. That is V0 DC. Okay, so as of now we are not focusing on the output voltage because it's a DC analysis. It's all about finding the Q points for the transistors T1 and T2 or Q1 and Q2. Okay, so this is 0. This is 0 means there is no current in this 50 ohm during DC analysis. Okay, 0 milliamps is going through this. Now let us find the currents existing in the emitters of Q1 and Q2's emitter, IE1 and IE2. Okay. So the problem is very easy from now. Here's what's the voltage across this 2.5K. The bottom is 2.5, the top is 5. So the net difference is going to be 2.5 volt. Therefore, the current in this branch is going to be 1 milliamps. Then here the top is 5 volt and this is 1.8. Therefore, the drop across this will be 5 minus 5 is higher potential, 1.8 is lower potential. 5 minus 1.8 will be 3.2 volt. 3.2 across 6.4 will make 0.5 milliamps. So you know your IE1, capital IE1, you know your, okay, this is IE2 and this is IE1. So the conclusion is capital IE1 is equal to 0.5 milliamps. That's a Q point current of transistor 1. And this is Q point current of transistor 2, that is equal to 1 milliamps. So we need to confirm both are active. So to be active, the emitter should be higher than the collector. So what is the emitter potential? 1.8, collector potential is 0. Therefore, Q1 is active. And similarly, Q2's collector is 0 and emitter is at 2.5. Therefore, we are able to prove that VEC1 is greater than 0 and VEC2 also greater than 0. Therefore, both the transistors are active. They can act as amplifiers in the given circuit. That's end of DC analysis. But we need a small parameter before getting into the AC analysis. Find out small RE1. For that only thermal voltage is given. So it's VT by IE1. And similarly, RE2 that is equal to VT by IE2. So thermal voltage is given 25 millivolts purposely. So 25 millivolts by IE1 is 0.5 milliamps. So 25 by 0.5 milliamps is going to become 50 ohms. That's a small RE1. And small RE2 will be 25 millivolt divided by 1 milliamps. So it is going to become 25 ohms. Okay. So with that, let us begin the small signal AC analysis. But in this case, it's not AC, it's a DC. Okay. Let us turn on the supply voltage, that is 10 millivolt. Okay. It's like a AC analysis. So let me label this as a AC analysis. Treat the small incremental change as a AC. Then switch off all the DC component. 5 volt is made 0 and this 2.5 volt should be made 0. This 1.1 should also be made 0 because they contributed only for the Q point earlier. Now let us bring the signal into the play. Then we'll find out what is the actual contribution by the entire circuit, that is your V0. So we need to find out that V0 only now. Okay. So this is made 1.1 volt battery made 0. The 5 volt battery is switched off and the 2.5 volt battery also switched off since they contributed for the Q point in the DC analysis. Now let us play for the equivalent circuit. Before that, we need to bring the, this is your transistor Q1, this is your transistor Q2. So you have to bring the small RE1 and small RE2. RE1 should be connected here. RE2 should be connected here for a comfortable small signal AC analysis. Then what else is going to happen? The circuit will get simplified. Okay, so yes, this 3.9K and 1.1K because of the top 5 volt grounded 3.9K and 1.1K will become parallel. Let me call this as RB1. Okay, for a kid, we'll play with that value. So what is RB1? RB1 is going to be 1.1 kilo ohm parallel with 3.9 kilo ohm. Okay, that's RB1. And let me call this as RC1 and sorry, RE1 emitter side of transistor 1. So I will call it as RE1 and I will call this as RE2. Okay, so with them, so we'll, and this is your something like your load, we can say. So we'll get the AC equivalent circuit as a function of RB1, RE1, RE2, and capital RL, and also along with small RE1 and small RE2. So we'll make a comfortable AC kind of analysis. Okay, so what is the equivalent circuit now? So we are going to have V in. This is the input voltage V in that is given. Okay, we'll play with that. That is given as 10 millivolts. Okay, so here we have RB1. Then the first BJT, it's a PNP transistor. Remember, the collector is already connected to ground. Let me take this way. And here we have the capital RE1. And this is already connected to the ground because it is connected to +5, that is switched off. So this is RE1, that is 6.4 kilo ohms. Then we have small RE1. Okay, let me keep it little down so that I can connect it to the next transistor comfortably. This is RE1. So here we have the base of the next transistor. That's another PNP. So this collector also connected to the ground. So this is the emitter. Here we have the small RE2. Okay, then we have the capital RE2. It's also connected to the ground. And here we have the output V0, and this point is connected to the RL, that is the 50 ohm resistor. RL is equal to 50 ohm resistor. This RE2 is equal to 2.5 kilo ohm resistor. RE1, yes. So we know the values of, yes, we are going to begin the AC analysis now. Okay, let me keep a copy of this. Yes, let us begin. So this point, as per the small signal AC analysis, this is your emitter point. Remember, this is your base point. And similarly here, this is the base of transistor Q2. This is transistor Q1. This is transistor Q2. And this is the emitter. Yes, that's a mistake I have committed. So I should have connected the V0 as per the circuit to the emitter. So therefore, it should be this connection. Okay, that's a connection. That's a small mistake. Yes, please correct it. Yes, there is no connection here. Yes, this is how the V0 must be connected. Yes, let us play now. So as per the small signal equivalent, this difference is equal to 0. Okay, that's how usually I mark. So you know where is the emitter and base. So this is actually the small signal. Okay, a virtual short kind of stuff. Similarly here as well, it is equal to 0. Okay, so not from base to emitter, this is your emitter, remember. Okay, that's where you take the output as your V0. Okay, then let us play. So this point is 10 millivolt, and also given that the input resistance of the BJT is infinity, that means the base current can be taken as 0. So the base current is 0. So there is no base current. So from 10 millivolt, anyway, the base potential is 10 millivolt and no potential difference. Therefore, this is also going to be 10 millivolt. Let me play with voltage straight away. It's 10 millivolt. RE1 is known. RE1 is 50 ohms, and this is 6400 ohms. And the current is going to be this way, and no current in this base as well. So let us find this point potential. I'll call this as Vx by potential division. So Vx is equal to, it's a voltage drop across what? 6.4. Okay, that's your Vx. So then it is going to be 6400 divided by 6400 plus 50 into 10 millivolts. That's your Vx. Okay, let it be. So this is Vx. I know I can calculate. And again, this is 0 means. And again, this is 0 means this point is going to become, yes, this point is going to become Vx. This point is going to become Vx. And then what is V0 means? Another potential division takes place here between small RE2 and capital RE2. Small RE2 known, 25 ohms, and this is 2500 ohms. Okay, so this is my Vx, and this is the output. What is V0? V0 is going to become Vx, and then the voltage V0 is going to be the drop across capital RE2. So that is equal to Vx into, what is that? Capital RE2, that is 2500 ohms, divided by the total, that is 2500 plus 2500 plus that 25. Okay, so that's your V0. Then substitute Vx in the V0. Then V0 is going to become, so let me substitute this and this. Yes, very interesting problem. Interesting small signal AC analysis. Then V0 is equal to, we'll straight away go for V0. V0 is equal to, yes. So this is a mistake. Remember that this is V0. There is no connection here. And this is Vx. So Vx as a function of your Vn, one potential division between the two, another potential division because of Vx coming here straight away. So that is going to make your V0. Okay. So the V0 is, so we are going to substitute Vx means then it is going to be 6400 by 6450. 6400 by 6450 into what? 10 millivolt into this number. So let me go for 2500 by 2525. 2525 into 10 millivolt will be the V0. Yes, time consuming, but still easy problem to connect. Okay, with a comfortable AC analysis, let me calculate the number. 6400 divided by 6,450. In fact, in the examination, you can cancel one digit. Okay. Then into 2,500 divided by 2,525 into 10. That will be your answer. So it is going to be 9.8242 millivolts. Okay. Yes. Up to how many decimal places? We'll check. The output voltage V0 with the small signal input voltage Vn equal to 10 millivolts. Okay. Rounded off to one decimal place. Rounded off to one decimal place means your answer must be, answer is equal to 9.8 is a perfect answer for this problem. Okay. And hope we have determined the best possible answer for this problem. So we have to play with the small signal equivalent of transistor 1, that is Q1, and transistor Q2 carefully. It's same as how you play with NPN. Okay, so the habit of playing with the PNP will help you there. Okay, so keep the emitter in the top itself, and so that you can verify whenever required whether the AC equivalent we have determined is perfectly all right or not. Then okay, it's easy verification as well, two potential division. So bring the two potential dividing factors into the play. This is one potential dividing factor. This is another potential dividing factor. So multiply with the input. That's your resultant. Okay, so it seems to be a perfect answer. So anyway, we'll verify once the answer key is released soon. Okay, and hope you enjoyed this content delivered. And you can subscribe our channel. You can also share to your friends. Okay, getting the answer key for biomedical is very difficult, so we are helping you. That's the reason. Okay, so first we are taking the hard problems, especially belong to the subjects circuits, analog, digital, controls, measurements, and sensors. Okay, so that's a problem you can expect in the beginning. So thanks for watching. Do subscribe our channel. Okay, so already the batches of biomedical started in our institute, and students, okay, so wants any guidance, please call us or do WhatsApp. We'll try to help you as much as possible. Thank you.